Alright gang, here we go. So this is Chem 2, Unit 3, and we're going to be talking about limiting reactants. Okay, so limiting reactants, and percent yield. Okay, so limiting reactants is the reactant present that's in the smallest stoichiometric amount. So this is really just a fancy way of saying this, that it's the reactant you will run out of first. Okay, so we've done this reaction like over and over and over again, right? With this idea that hydrogen and oxygen can combine to form water. And if we were going to balance this sucker, we'd need 2 waters, which would mean we need 2 on the hydrogen, right? So we've looked at this reaction a ton of times. So if we had 10 molecules of hydrogen and 7 molecules of oxygen, then we could combine them, but in order for this to work, every 2 hydrogens need to combine with every 1 oxygen. Okay, and so this will turn in, so all of our hydrogens will be used up, but only 5 of the oxygens will be used up, because in order for these 10 hydrogens to be used up, it only takes 5 of these oxygens. So we'll still have 2 oxygens left over on this side. So notice how the hydrogens here, the white ones, got turned into waters, and we still got 2 oxygens left right there and right there. There's no hydrogens left over. So because hydrogen is what we ran out of first, okay, it's the limiting reactant, okay, and the oxygen is because it is what we have left, so it's the excess reactant, okay, so the oxygen would be the excess reactant. All right, so the limiting reactant is what we're going to use in all of our stoichiometric calculations. So anytime you're given a set of a reaction that has several different reactants and they give you amounts for each of those, you kind of have to do a limiting reactant problem always to start it, just to figure out which one reacts first. And then from there, you can move forward and solve whatever else it's asking for. All right, so let's do a practice problem here. I don't like that one. Let's do this one here. So we've got 1.5 moles of aluminum and 3 moles of chlorine combined in this reaction here. Okay, 2Al, which is the limiting reactant. Okay, so so it says we've got 1.5 moles of aluminum and 3.00 moles of Cl2. And so it asked us, it says which one is the limiting reactant. So which one's going to run out first? So we got to just turn both of these into one of the products. Since there's only one product, then we're just going to convert it into that. All right, so we're going from moles to moles, right? Because we got moles here, we're going to convert it to moles of this. So we'll put moles of aluminum in the bottom, and we'll put moles of AlCl3 in the top. Okay, so 2 moles of Al to 2 moles of AlCl3. So that's 2 over 2, which is 1, so that we get 1.50 moles of AlCl3. So that's how much AlCl3 will make if our aluminum reacts all the way. Now we have to see if chlorine will make more or less. All right, so now we're going to assume our chlorine is going to react all the way. So we'll put moles of Cl2 in the bottom, and we're going for 2 moles, oh my gosh, moles, why, of AlCl3 in the top, mole ratio, so there's a 3 with the Cl2, and there's a 2 with the AlCl3, so we take 3 times 2/3, it's going to be giving me 2, isn't it? 2 divided by 3 times 3. Yeah, I don't even know why I had to plug that in, that was silly. So we get 2.00 moles of AlCl3, all right? So because the aluminum makes less, the aluminum has to be our limiting reactant. Okay, so the limiting reactant is aluminum. Okay, how many moles of AlCl3 are formed? Well, it's going to form 1.50 moles of AlCl3. All right, so that answer is right there. Okay, how many moles of excess reactant remain at the end? So the excess reactant, in order to find that, we need to figure out how much Cl2 is going to be left over. All right, so there's a couple ways we can go about this. The easiest way I find is take the amount of a product that we could have made, which is this 2.00 moles of AlCl3, and we'll subtract out the moles of what we actually made, which is this part here. Okay, so we'll take 2.00 minus 1.50. So there's 0.50 moles of AlCl3 that could have been made. Okay, but we ran out of aluminum. So that's the AlCl3 that could have been made by the Cl2. If we convert this into moles of Cl2, we'll know how many moles of Cl2 are left over. Okay, so set up our parentheses. We'll put moles of AlCl3 in the bottom and moles of Cl2 in the top. Okay, mole ratio here, 3 goes with Cl2, 2 goes with that guy, so it's 0.50 times 3 halves, so it would be 0.75 moles of Cl2. Okay, so that is the excess right there, 0.75 moles of Cl3, 0.5. Let's just do it times 3 halves. Yeah, all right, cool. All right, theoretical yield, all right, is the maximum amount of product that can possibly be made. All right, so like that's assuming everything went exactly smoothly and in the lab and we had everything worked out and like we lived in a perfect world. Theoretical yield is what the math says we should make. Okay, all right, so this is what the math says. All right, what the math says. Okay, the actual yield is what we actually get. Okay, what we actually get in the lab. So never are we actually going to get what our theoretical says we should get. We should get close as long as we're following proper laboratory procedures, doing everything exactly right. We should be really close to that value. Okay. Now percent yield, in order to find percent yield, okay, we're going to take the actual yield divided by the theoretical yield times 100. So it's kind of like finding your percent on exam. You take what you got on the score, what your score was, divided by what your score should have been, and then multiply it by 100. Okay, so the percent yield is essentially just how good of a job did you do getting what you should have gotten. All right, so here's a tough problem, and this kind of walks us through everything we've done so far in this chapter. So if you can solve this problem on your own, then you're pretty much golden for the test, in my opinion. Okay, so here we go. So we've got hydrogen sulfide gas. Okay, and it's bubbled into a solution of sodium hydroxide, and reaction forms sodium sulfide and water. Okay, how many grams are formed? So 1.25 grams of hydrogen sulfide is bubbled into a solution containing 2 grams of sodium hydroxide, assuming that sodium sulfide is made at 92% yield. All right, so first step always is to write out a balanced chemical equation. So hydrogen sulfide gas. All right, so we've got H and S. Well, the charge on a hydrogen is +1. Charge on a sulfide is 2-. So that means we need 2 hydrogens for each one of those. So we got H2S gas, all right, reacts with sodium hydroxide. So that's NaOH. And it says it's bubbled into a solution. So that means it's aqueous. All right, bubbled into a solution. All right, that's aqueous, and it forms sodium sulfide and water. So that'd be Na and S, and this is kind of the same situation. S is 2-, and sodium is 1+, so we need 2 of these guys, so Na2S. All right, and reaction forms sodium sulfide. Honestly, I don't remember if this is a solid or a precipitate. Oh, it's got sodium. It's got to be in solution. Never mind. All right, and also water. All right, everybody should know what water is. So that's liquid. So all right, so there's our chemical equation. Now we got to balance this sucker. All right, so we've got 1, 2, 3 hydrogens over here and 2 hydrogens over here. So let's wait on the hydrogen, see what else we can dig up before we start messing around with that. We got 1 sulfur, 1 sulfur. Okay, 1 sodium, 1 sodium. So we'll put a 2 here for now. So 2 sodiums, and now we've got 2 oxygens. Oh my gosh, this is going to be a thing, isn't it? All right, so we've got 2 oxygens, so that means I need 2 oxygens here. All right, now we've got 4 hydrogens. 1, 2, 3, 4 hydrogens, and 1, 2, 3, 4 hydrogens. Oh, thank goodness it worked out. All right, so let's double check it real quick. Got 2 hydrogens, 4 hydrogens on this side, 4 hydrogens on the reactant side, and 4 hydrogens on the product side. 1 sulfur, 1 sulfur, 2 sodiums, 2 sodiums, 2 oxygens, 2 oxygens. All right, so we're balanced. Now we have to figure out, so this is our balanced chemical equation. First step. All right, now we have to figure out which one our limiting reactant was, because we want to figure out how many grams of this sodium sulfide can we make. All right. So we've got 1.25 grams of hydrogen sulfide, so 1.25 grams of H2S. All right, and we got to convert that into grams of sodium sulfide. All right, so here we go. We could just take it to moles or to grams. It doesn't really matter. We're going to end up doing the calculation anyway for one of them, so we can, whatever floats your boat, you could go either way. Grams of H2S to moles of H2S. All right, so we put 1 up here. Now we got to figure out the moles of H2S. So H2, so we got 2 hydrogens and 1 sulfur. All right, so we got 2 times 1.01 plus sulfur is 32.06. All right, so 2.0. I don't know why I always reach for the calculator when I can do things in my head just as good. 34.08. All right, 2.0, 34.08. All right, 34.08 grams per mole. All right, so that's the molar mass of our H2S. Now we got to convert it into moles of Na2S. All right, because that's what we're trying to find, is sodium sulfide, right? That's the product we're after. So we'll put moles of H2S in the bottom and put moles of Na2S in the top. All right, molar mass is here, so we've got 1 of Na2S and 1 of H2S. So we'll put 1 and 1. All right, now we're in moles of Na2S. Now we've got to convert it into grams of Na2S. So we'll put moles of Na2S in the bottom, put grams of Na2S in the top for every one. So now we got to figure out the molar mass of Na2S. All right, so we got 2 sodiums and 1 sulfur again. All right, this one I'm going to need a calculator for. 2 times 22.99 and 32.06. All right, so we take 2 times 22.99 plus 32.06, 78.04. So that's the molar mass of this guy here. So 78.04 grams of Na2S. All right, now we can take this whole guy and plug it in our calculator. So 1.25 divided by 34.08 divided by 1 times 78.04. And you got 2.86 grams. 2.86 grams of Na2S. All right, so if our hydrogen sulfide reacts completely, it'll form 2.86 grams of sodium sulfide. But first we have to make sure we have enough sodium hydroxide in solution to make that happen. So now we're going to react our sodium hydroxide and see how many grams of sodium sulfide we can make. So we're starting with 2.00 grams of NaOH. All right. So we're going to draw our parentheses. So we put grams of NaOH in the bottom and moles of NaOH in the top. All right, so for every 1 mole. So now we got to find the molar mass of sodium hydroxide. See how much fun this is? So we got 1 sodium, 1 oxygen, 1 hydrogen. All right, so we take 22.99 plus 16.00 plus 1.01, should get 40.00. All right, so 40.00. All right, so now we're going from moles of sodium hydroxide to moles of sodium sulfide here. So that's going to be 2 for every 2. We get 2 moles of sodium sulfide for every 1 mole of sodium hydroxide. All right, so that's that guy there. And then we need to convert it into grams of sodium sulfide. So we'll put moles. Thank goodness this step is the exact same as the one that came right above it. So 78.04 grams of Na2S. All right, so we take 2 divided by 40 times 2 times 78.04. We get 7.804 grams. These numbers are feeling off. Oh, never mind. I was looking at a different problem. All right, 7.804 grams. 7.804 grams of Na2S. That sig fig's not right, so it should be just 7.80 grams. But regardless, it doesn't really matter. We're making our sodium hydroxide is going to have way excess reactant. So here, this is our limiting. Okay, so this is how much we can actually make. So this here, this value 2.86 is our theoretical yield. theoretical yield. All right. All right. So that's our theoretical yield. Now our percent yield, okay? Now remember, so we want to find out how much we're actually going to form. So our percent yield, right, is equal to the actual yield divided by the theoretical yield times 100. Okay. Now we know that the actual yield is the theoretical yield is the 92%, and we're trying to find the actual yield. So we're going to set this equal to 92. Okay. So 92 is going to be equal to the actual yield, which is what we want to find, divided by the theoretical yield, which is this 2.86. Okay, 2.86 times 100. Okay, so we divide both sides by 100, multiply by 2.86. So our actual yield is going to be equal to 0.92 times 2.86. Get 2.633 grams of Na2S. So this is how much we could actually form. Cool. So that was a lot of work just for a little bit of problem here, right? And it's just, a couple sentences, and we got to spend 10 minutes together solving it. So anyway, let me know if you have any questions here. It's quite a bit, but just keep on keeping on. Just work it through step, find that balanced chemical reaction, plug things in, solve for your limiting reactant, figure out which one solves first, and then just keep on keeping on just straight through the steps. You can do it. All right, let me know if you have any questions.